Hey everyone, so we come back to standardization and I'm going to show you a quicker method for our standardization. Now this method mainly comes from the further math chapter of confidence interval, although that method or that particular method taught in for that particular chapter actually is derived from our confidence interval. Now what do I mean? Alright, so let's take a look at a few examples and we start off with again a generic example of x holding a normal distribution with mu and sigma squared. Alright, so let's say we have Px bigger than A has a probability of B, where we have B being between 0 and half. Alright, now from here we know that, well, A must lie to the right of the mean, because if we were to draw the normal distribution graph, then you know that if the mu is in the center, I mean mu has to be the center, it is the mean after all, then, well, for x to be bigger than a to have a probability of less than half, we know that the probability to the right and left of the mean are half respectively. If it's less than that, less than half, you know that a would be somewhere around here, right? And this would be, well, b, okay? But here's the thing, because we're dealing with variables, so what we'll do is, we will then do standardization, where we now have the mean as 0. So what happens to our value of a? We know that now Px bigger than a is the same as Pz bigger than a minus the mean over whole thing over sigma, and this probability still equals to b. So at the same spot, but now this part is a minus mu over sigma, and this we know that equals to the inverse norm of b right. Okay, so we can actually then from here equate it as a minus mu over sigma equals to the inverse norm of b, which is zb. Alright, and this is always a positive value in terms of representation. Of course, it's possible to get negative value, because if we change this to left, then you get a negative value. But when we talk about z subscript b or z subscript any probability, we're looking at the positive value. Alright, aka the value on the right. Then from here we know that we have a equals to mu plus zb sigma. And actually, you notice that for every type of standardization, that for the value that lies on the right of the mean, this will always give you this particular equation, where you can actually jump from this equation 1 and then derive equation 2. Likewise, if we let's say have Px less than alpha for probability of beta, where again beta is between 0 and half, we now know that the value of alpha, right, let's say we do after standardization, this particular value will lie to the left of the mean. And this equals to, well, negative, right? Because this is 0, the mean is at 0. The value to the left would then be negative, hence negative z beta. Don't forget z beta is always, or rather the inverse norm, where we represent as z subscript anything, will always be a positive value. As such, we have a negative sign right here. Therefore, we can then get a similar equation where, after doing many manipulation, I'm going to do it actually to show you how it's derived. So we know that this equals to minus z beta. Alpha then simply equals to mu minus z beta times sigma. Alright, and you notice that there are similarities between this equation here and this equation here. You notice that whatever value that's inside the probability would simply be the mean. Alright, so I'm just going to write it in a generic form. So whatever this value inside, let's say we have now Px less than c, then you notice that it's always c equals to mu plus minus z, let's say this has probability d, z d sigma. Now, why plus minus? Think about it. Your value of c can either lie on the left of the mean, which is then less than the mean, or the right of the mean, which is more. So if it's less than the mean, you will get a minus sign. If it's more, you'll get a plus. Alright, and that depends on the probability of d. If D has a probability greater than half, well, then we know that C has to lie somewhere around here, right? Because for C to lie around here, then you have a probability that's less than or more than half, right? So it really depends on the probability given. The idea is that in order to use this method, one should strive to get this probability to be between 0 and half. All right, so in conclusion, okay, so if we have x following normal distribution mu sigma square, and we have, let's say, px bigger than a equals to, let's say, probability b, and let's say we have b that is between 0 and half, whoops, we know that we can simply get a equals to mean plus zec b sigma. If we now have px less than alpha equals to beta, where we have beta is between 0 and half, we can then get alpha equals to mean minus zec beta sigma, with the parent equation as whatever you have inside is equals to mu plus minus zec probability. So usually it's given as alpha, but let me use another Greek letter, gamma sigma, where this is your mean, this is the probability, and then sigma, and plus minus is depending on whether the value lies in the left or on the right. Alright, so this is how we use standardization and quickly obtain an equation that uses it, and then basically saving us a lot of time by skipping 1 or 2 steps. And this is particularly useful for hypothesis testings and for your sampling as well. It saves a lot of time to have to go through inverse norm and then do a lot of sorts of algebraic manipulation. You can just simply solve your hypothesis testing in 1 or 2 steps after writing that long essay. Alright, and I'll show you that in the next video when I tackle a particular normal distribution problem that would use standardization.